Today we will study about acidic and basic strengths. Just to remind about the definitions. One very important definition which we will see is the Bronsted acid-base theory. This is most useful here. So according to Bronsted-Lowry acid-base theory, tells us that a proton donor is an acid. Proton donor as an H plus donor is an acid, and proton acceptor H plus acceptor is a base. And any acid HA, if it releases H plus, and if this is an acid, the leftover negative part will be conjugate, right? So these are few pointers we must know before we start the comparison of acidities. The third important point is stronger acid or stronger bases are unstable. They are unstable, which means the reason for using the word stronger signifies that those particular species are unstable. So they will try to move on to more stable state. All right. Next, a strong acid and a strong base reaction would normally be one-sided. It will always give you weak conjugate base and weak conjugate acid. It is mostly irreversible. While if you take stronger acid, weaker base, or weaker acid, stronger base, both would exist in equilibrium, where this will form weak conjugate base and strong conjugate acid, while this would form strong conjugate base plus weak conjugate acid, and they would be reversible. Okay. And another important point when you discuss about Bronsted-Lowry acid and bases is that stronger acid will give weaker conjugate base, and weaker acid will give stronger conjugate base, and vice versa. Like in case if you have a base, the stronger the base, weaker its conjugate acid would be, and weaker the base, stronger its conjugate acid would be. These are some simple terms you must know before starting with the acidic strength analysis. Okay, students. Now, most of the organic acids, organic bases, they are not very strong, right? Neither they are too weak. So most of those would fall into these two categories. So where we might be dealing with a strong acid weak base or a weak acid strong base. Weak acid weak base, we generally don't see that reaction happening that easily. And suppose in case if we have strong acid and strong base, the reaction will give you weak conjugate base and weak conjugate acid. The backward reaction is normally not very favorable. So this is not very favorable. thermodynamically. Got it? Which brings to the next important concept, that an acid can be defined as kinetic acidity or thermodynamic acidity. So it could have two types of, there are in fact two categories of acidities which we can define. For example, if we have an acid like HA, a generic acid, and these definitions we will always consider mostly in acidic solutions. Now imagine Ha plus H2O is giving, a rate constant K1 to give H3O plus and A minus. So it's clear that it is an acid and this is a conjugate base. This K1 represents rate constant in the forward direction, K2 represents rate constant in the backward direction, and the equilibrium constant Ka represents K1 by K2, which is the dissociation constant of acids or ionization constant of acids. Most of the time we will be discussing about, either by comparing Ka or by comparing pKa. Just like pH is defined as the minus log of H plus concentration, pOH is defined as minus log of OH minus concentration. Similarly, pKa is defined as minus log of Ka value. So whatever the value of Ka comes across. So from here it is evident that if Ka value is more, pKa value would be less. And if Ka value is less, pK value would be more. Suppose if Ka value is more, which means it is more acidic because there is more dissociation towards forward direction. If Ka value is less, it means it is less acidic. Less acidic. So from here we can conclude that strength of an acid is directly proportional to the value of Ka or inversely proportional to the value of pKa. So if pK value is more, which means it is a weaker acid. If pK value is less, we can say it is a stronger acid. So henceforth, we will try to always compare the pK values of acids. Okay, students, just make sure you have a note of all these synopsis. Finished. Now, we always see acids as either kinetic acidity or thermodynamic acidity. Thermodynamic acidity. What does this mean? Suppose if we have an acid HA, in HA, if the electronegative difference between these two is quite high, okay, which means high electronegative difference between H and A, then we call it kinetic acid, which means it would have more kinetic influence than thermodynamic influence. Okay, what do you mean by kinetic influence? It mainly depends upon how faster this can give H plus rather than what stable compound it is giving or not. Got it? For example, if we have more electronegative elements like hydrogen connected to nitrogen, or hydrogen connected to oxygen, or hydrogen connected to fluorine, here you can say that the electronegative difference is very high. Okay, so in these cases, right, we observe kinetic acidity. Which means if you have any stronger base, okay, any stronger bases, like B minus, any B minus, I'm writing it as a generic form, will definitely extract, proton from it. It will extract proton from it, and it will become BH plus A minus. Got it? Where this has delta positive, delta negative. What are these B minus bases? Bases which could be simply as simple as a metal. Okay, 2 moles of, for example, if we have 2 moles of potassium or 2 moles of sodium, they will give electrons to hydrogen, and hydrogen will escape as hydrogen gas, which means this is acting like an acid. Electrons are being provided to it and it will escaping like an H2 gas. Or we can have H minus, that is hydrides. Hydrides come from, metal combinations, ionic hydrides like KH or K plus and H minus, or Na plus and H minus. And either we should have very strong bases like ETO minus K plus, okay, any RO minus to that matter, CH3O minus K plus, or any simple alkyl group also, CH3 minus all carb anions, CH3 minus lithium plus, PH minus lithium plus, okay, CH3 minus MgBr plus, right, or tert-butoxide O minus K plus, right, N Bu minus Li plus, N-butyl, lithium N-butyl. Or another very important base which we will be using a lot of times is N minus, like this, with Li plus. This is called as LDA. We'll be using this very exhaustively. Okay, LDA, lithium diisopropyl amine. LDA, diisopropyl amine. These are all very strong bases. They will extract proton very easily and convert into their respective conjugate acid. Okay, students. Now, when we are looking at the stability, this is one way of looking at an acid, like we observe the kinetic acidity, which means we are only concerned about what is the electronegativity difference between hydrogen and the connected atom. Got it? Now, suppose if we observe A minus stability, that is conjugate base stability, got it? Then we say it as thermodynamic acidity. Thermodynamic acidity, which means you are discussing about an acid on the basis of its conjugate base stability. Understood? For example, if at all, imagine this way, HA is a strong acid. SA means strong acid. Suppose after dissociation, it has become weak conjugate base. Now I will check out the strength of this. The more stable the A minus is, which means it is thermodynamically more stable. If this is more stable, the reaction must have driven in the forward direction easily, which supposed to mean that HA is strong acid. So from here we can say that, okay, more stable conjugate base implies strong acid. Got it? So we will compare the stability of those conjugate bases and then discuss whether the acidic nature, whether the acid has more strength or less strength. Okay, this way of comparing is called thermodynamic acidity. If you are only comparing on the basis of electronegativity of HA, then we call it as kinetic comparison or simply a kinetic acidity comparison. In case if you check out on the basis of stability of the carb anion, sorry, on the basis of conjugate base, then we call it as thermodynamic acidity. To compare the acidic strength, what are the traits we would do? First, we will release the H plus released. After releasing H plus, we will get an anion, which is a conjugate base. This is a conjugate base. So this is what we will get. So imagine we got this one. First, we got a conjugate base. So from conjugate base, I will check out for two important things. One, either the charge, if you check out the anion charge, whether the charge is identical, are we comparing between the identical atom? So if negative charge is on identical atom, like you are comparing two acids, both of them has O minus charge on it. That is the first thing you are checking out. Okay. Or in case if not, that is not the case here, then in case if you are just checking that if there are negative charge on two different atoms, so that is negative charge on two different atoms. In case we have two different atoms, the only thing that I will compare is first factor is electronegativity. If it is across the period, if those elements belong to the same period, I will always compare electronegativity. If that is not the case, I will check out size across along the group. So these are the two comparisons which I will do. For example, if at all I talk about group, like I compare HF, HCl, HBr and HI. So I will get the conjugate bases as F minus, Br minus, Cl minus, I minus, right? So I will be comparing their sizes. If it is about left to right, like I have CH4, NH3, H2O, HF, then I will compare them across the period. Got it? Now suppose if the charge is same, okay, I mean if the atom is same, then I will check out the first point difference here. We will check first point difference, first point of difference. Okay, which means in case if you have negative charge, right, where there is either a pull or push of electrons, then I will see there is a percent, what is a percentage S character present on it, correct? Or what is the electronegativity difference there, or if there is any plus or minus I effect which is present. Just by pulling off electrons, sigma electrons, then I will check out these three characteristics. Either it is percentage S or electronegative difference, or plus inductive or minus inductive effect operating on it. Suppose in case if we have negative, here negative charge is not just about push or pull, it is about a complete dispersion. Negative charge is dispersed. Then I will check out first, is there an aromatic nature? So aromaticity is something we will check. Next, we will compare, is there any resonance that is favoring the conjugate base, or is there any equivalent resonance also? Equivalent resonance. Okay. Then if there is any d orbital resonance, these are the comparisons which we will do to exactly find out which is more acidic and which is more basic. Okay, students. So this is the brief synopsis of how we compare the acidic strength. Now, let us go factor by factor. What would be the factors that would affect the acidity? So first, we'll discuss factors affecting acidity. So first factor that affects is the strength of HA bond. Second factor is polarizability of HA bond. Third factor, electronegativity of A. Fourth factor, stabilization of A minus, that is conjugate base. Fifth factor, nature of solvent. These are all the influential factors for acidity. Out of which, let us see the first case here. For example, if at all I am going across the period, like I have CH4, NH3, first one is group 14, then group 15, group 16 hydride, and group 17 hydride. I'm supposed to compare the acidity of these four. Across the period, I will always compare electronegative differences. So this is across period. Across period, always compare electronegative differences, which means you are comparing kinetic acidity. Now you can see that HF being more electronegative difference, that would be more acidic than the others. So it's clear that more delta E electronegative difference implies more acidity or more acidic strength. In fact, if you check out the pKa values, I told you that pKa values will help us understand, whether it is more acidic strength or less acidic strength. So if you compare the pK values of all of these, methane is approximately around 50, ammonia is around 38, water is around 15.5, and HF is 3. So you can see that higher the value of pK value, less will be the acidic strength. Smaller the value of pK value, more will be the acidic strength. Now suppose if we go down the group, for instance, if we have HF, okay, HCl, HBr, and HI. As you go down the group, you should always consider the increasing size. So down the group, if you check out strength, that is acidic strength, check out the acidic strength. HI will be more acidic than HBr, then HCl, then HF. So here we are considering the size of the anion, correct? So larger the size of the anion, okay, which implies more acidic strength, right? Another example in that line would be, how we have H2O comparing with H2S, comparing with H2Se, comparing with H2Te. So if you see in the group, the acidic strength will always increase. Now if you check out the pK values, the pK values for these are important. HF, we just learned that pK value is +3. HCl is around -7, -9, minus 11. So HI is considered to be one of the strongest acids with pK value of minus 11. If you see, as you have if you are to compare left to right in an period, in case, let's say if at all I have SiH4, PH3, H2S and HCl. This is from the third period. Got it? So in case if you are considering from the third period, this is how the acidic strength would be. So acidic strength will increase from left to right. Always remember, in a periodic table, left to right, the acidic strength will increase. Down the group, acidic strength increases. Now, suppose if you have alkanes to compare, like CH3, CH3, ethane, CH2, CH2, ethene, CH triple bond CH. So if you are comparing hydrocarbons, right? In that case, we will consider the percentage S character. So more the percentage S character, more percentage S character, more acidic strength. Got it? So now if you consider between this carbon and hydrogen, this carbon and hydrogen, and this carbon and hydrogen, and check out their respective pK values. The pK values here, you can see ethane is approximately around 48. This is around 44. And this is around 25. So it clearly tells us that ethynes are more acidic in nature. Right, the next one. Suppose if you are comparing cyclopropane with cyclobutane. So here we are considering, the hydrogen, this hydrogen bond with this one. Now, which one being more acidic? We have learned that when it comes to exo bonds, S character is more in them. So here we can say the percentage S character is more in exo bonds. Hence, which one will be more acidic? This is how the acidic strength would be. So when you compare cyclopropane, this is what acidic character would be. Now if you check out its pK value, in fact the pK value of cyclopropane is around 46. Which means if we compare generic alkanes, it is better than straight alkanes. Got it? Next, if we consider, heterocyclic molecules like this, we have H and H with plus charge here, and then we are comparing N, H and H. The same logic here also. If you check out this exo bond and you compare with this exo bond, in both the cases, percentage S character would be more for this one. So therefore, it is on the basis of percentage S character in exo bonds. Now coming to the types of acids. When it comes to simple acids, all carboxylic acids, HCOOH, CH3, COOH, CH3, CH2, COOH, and put it this way, CH3, CH3, CHCOOH, and CH3 thrice CCOOH. Okay. Now if we consider the acidic strength in all of them, we have to check out how the inductive effect is. You can see we are comparing with hydrogen with one methyl isopropyl to that of tertibutyl. Correct. Okay. So you can see tertibutyl will have most amount of inductive effect. So from here, we should put one thing in our mind, that more the plus psi effect in any species, less is its acidic strength. less is its acidic strength, and more the minus I effect, more acidic strength. Okay. Why it is, you can discuss that on the basis of conjugate base also. For example, if I take H C double bond O minus, this is conjugate base. CH3 C double bond O minus. Okay. See, this is showcasing an equivalent resonance. You remember this. C double bond O minus has an equivalent resonance. Now suppose any push of electrons towards it will only destabilize its equivalent resonance. So if the equivalent resonance strength is decreasing because there is some electrons are being pushed towards it, that would decrease its stability. So if this species becomes less stable, which means this CH3COH is less acidic. Everybody understood this point, right? Always compare with the conjugate base stability. If conjugate base is becoming less stable, which means its respective acid from which it is coming is less acidic. Okay. So in short, in case if we compare all of this CH3COO minus, got it? I'll write it here, and CH3COOH, like this it is connected, imagine. COOH, CO minus. So these are all the respective conjugate bases. So we know that if we check out the stability of this conjugate bases, we have studied this already, how to compare the stability. This one will be more stable. HCO minus will be more stable. Since this is more stable conjugate base, the respective acid will be more acidic. So if we check out the acidic strength, this is how it varies. Okay, students, if we compare the pK values of the same, correct, formic acid has approximately around 3.8 pK value. Acetic acid, you may have compared this in ionic equilibrium a lot of times. It is around 4.76. Isopropyl acid has 4.86. Tertibutyl carboxylic acid has around 4.88. If you notice something, correct, most of the carboxylic acid will range maximum up to 5. Most of the carboxylic acid in generic, they will range anywhere from 1 and they will come maximum towards 5. Got it. So if you were asked generically what is the carboxylic acid's approximate pK value, it is anywhere close towards up to 5, or rather always less than 5 but not above 5. Now if we consider next comparison, suppose if I take COOH, COOH, this is oxalic acid, then I have HCOOH, then I have benzoic acid, COOH, and I'm comparing that with acetic acid, CH3COOH. Correct? Let me put the conjugate bases for all of them. CH3CO minus, COOH, HCO minus, here benzoate, CO minus, acetate, CH3CO minus. What are the effects we can see here now? See, COH is giving minus a effect. H is not showing any kind of effect. Benzene, see benzene what it shows. Benzene will show slightly amount of minus a effect. Okay. At the same time, if you check out benzene, we have C double bond O minus this way, which means this pi bond can also delocalize towards this, which means it is also showing plus M effect. It is also showing plus M effect. But benzene's plus M effect is not very effective. But in case if we compare its plus M effect with respect to its minus M effect, the plus M effect is slightly dominant. Okay, it is very slightly dominant. And when you have CH3O minus, it will only give you plus I effect. So overall, if you check out the cases, here it is withdrawing, completely withdrawing, electron withdrawing. So let me write down that this species is electron withdrawing group. Here benzene is slightly electron donating group. Here also it is electron donating group. So you can always see that electron donating group will decrease the acidic strength, while electron withdrawing groups will increase the acidic strength. Now if you even compare the stability of all of these four, this one being more stable than this, these are the stability of the conjugate bases. And respectively, if you check out their acidic strength, oxalic acid is more stable than formic acid. I mean, more acidic than formic acid, than benzoic acid and acetic acid. Okay, you can remember it like OFBA. Okay, if you recall Aufbau's principle, from that write this off as OF off, bow as BA bow. Correct. So simply remember it this way: OFBA, oxalic acid, formic acid, benzoic acid and acetic acid. Structure is like this, no? C double bond O, OH, and that is connected to C double bond O, O minus. How does that happen? O as in oxalic acid, F formic acid, B benzoic acid, A acetic acid. This is the order in which the strength lies. Okay. Just like how you remember Aufbau's principle, just remember it like in OFBA. Out of this Aufbau's, remember it like OFBA. Aufbau. Right. 1.25. Then you have 3.8. This is 4.2 and this is 4.76. These are the pK values. See, pK values are not to memorize, got it? But this will give you a clear idea about, you know, what we are discussing really matches with the experimental. Sorry. Next, if we consider CH2 COOH with, you know, different groups here. Suppose X is there. For different X value, we may have different acidic strength as well. So if at all I take X is equal to hydrogen, or X is equal to, X is being fluorine, if it is chlorine, okay, iodine, and if it is NO2, if it is NMe thrice plus, okay, this is how it is. Or in case if you have cyanide, in all of these cases, if you analyze the pK value, you can check about it. In case if this X is H, that will be acetic acid, and the pK value of acetic acid is 4.76. If it is fluorine, the minute it becomes fluorine, now we will have minus I effect. So here minus I effect will be dominant. So therefore it would be, I'll not write here, it will confuse. So 2.5, let me write out here, minus I effect. So acidic strength is increasing because of minus I effect. Chlorine does not give as much minus I effect as that of fluorine. So same reason, but the minus I effect of fluorine is better. Same way if you see bromine, oh, I didn't write bromine. So in case if it is bromine, the value is around 2.90. For iodine, it is 3.15. So for NO2, it is 1.68. For NMe3 thrice, it is 1.86. For cyanide, it is 2.47. In fact, the minus I effect experimentally has been checked on the basis of the pK values of the respective acids. So from here you can easily confirm which has most amount of minus I effect, students. This one, right? Nitrogen with 3 methyl groups and positive charge. And I've been always telling you that any species which possess positive charge will effectively always have very high minus I effect. Got it? Now, only between these two there is slight difference. NO2 and NMe thrice. You would see NO2 has slightly more acidic, more minus I as compared to that of NMe3. That is a slight exception that I will discuss it in some time. Okay. Other than that, you would see the acidic strength goes as per the nature given. Check out here. In case if we have CH2COOH, okay, so I'll just put it down as the order here now. Comparing all halides. So if you compare all halides, what we have just seen, suppose if you have CH2COOH with fluorine and CH2COOH with chlorine, CH2COOH with bromine, and CH2COOH with iodine. You can see this is how the acidic strength has been. Now suppose if the number of chlorines or bromines are increased, then what would happen? For instance, if we check out CH3COOH, CH2COOH with one chlorine, CHCOOH with two chlorines, and CCl3 with COOH. All three chlorines have been replaced in hydrogen. If you observe the pK values now, as you start increasing more the withdrawing groups, the acidic strength drastically increases. In fact, now you would see 4.76 moving towards 2.86, towards 1.25 and 0.65. So this has become highly acidic now. So trichloroethanoic acid is quite acidic. It is around 0.65 pK value. Right? This is on the basis of increasing minus I effect. What beta? Oh, sorry, reverse order. This, yeah, this is more acidic. Now, suppose if we compare on the basis of distance, if you see COOH with chlorine here and COOH with chlorine here and COOH with chlorine here. In all the cases, it is withdrawing only. See, even if you have one withdrawing group, it will make the entire group to be withdrawing only. So all of them, there is minus I effect only happening. Here also there is minus I effect. Here also there is minus I effect. Here also there is minus I effect. But effectively, which is giving more minus I effect? Where the chlorine is closest. Right, students? So suppose if at all I call this as A, B and C. Now how does the acidic strength vary now? Correct. So A greater than B greater than C. If we check out their respective pK values also, that will showcase that they are quite closer in terms of their acidic strength. Okay, so this is around 3.2, okay, 3.6 and 4.4. Next, if you check out in terms of more number of COH groups, or if you have dioic acids and there are alkyl groups in between, for instance, you have COOH and COOH. This is oxalic acid. And then we are comparing COOH with one CH2 and COOH. This is, what do we call it? Malonic acid. And if you have COOH and there are two CH2 groups in between them, that is succinic acid. Correct. Right? Now if you compare the acidic strength here, same is the case, just like what we have studied here. Distance, COH is a withdrawing group. As it keeps going far away from it, the acidic strength decreases. So again, you will see the acidic strength would be like this. And if you consider their respective pK values here, pK value of oxalic acid is 1.23, this is 2.83 and 4.19. Next, in case if we have any double bond or triple bond group present and comparing that with alkyl, like CH2 double bond CH CO minus and CH triple bond C CO, I mean COOH and COOH. If I compare this one, here you can see this is actually giving plus I effect, correct? Here CH2 double bond CH is slightly giving minus I, okay, as it would have COO minus here in the conjugate base, while here also it is strongly giving minus I effect. Got it? So here CH2 double bond CH may slightly give resonance also, but that is almost ignorant. Mostly it is the minus I effect which is slightly dominant over it. So now if you consider the acidic strength here, this is how the acidic strength would be. And if you check out the pK value here, pK value of propanoic acid is 4.76. Okay, sorry, 4.78. Sorry. And this is 4.28 and 1. No, not at all. Like I said, it is only for your reference. Tomorrow, while you're revising, it would be really helpful. Correct? Somewhere you have to compare maybe like, this acid with some completely vague acid like this, NO2. Correct? Clear? So not that you would be asked, at least you will have the data to compare, because this data is completely disposed over multiple books. So we collated all PKs at one place. Okay. Resonance will only decrease, na beta, stability. Suppose if you have this way, C double bond O minus, correct? This is already an equivalent resonance. So if you try to support any resonance, that will destabilize it. So let us compare the next one. If we have CH3OH, that is methanol, compare with ethanol, compare with isopropanol and tert butanol. Got it? Here also, if you see the acidic strength, no, methanol would be more, right? It will decrease again here on the basis of plus I effect. Next, suppose if we have, methyl, that is neopentyl carboxylic acid, and if you compare that with neopentyl silyl carboxylic acid with silicon present instead of carbon, if it is silicon present in it. Okay, is second one greater or first one greater? Check. Okay, if you consider this between carbon and silicon, which is more electronegative? Carbon is more electronegative, which means silicon is more donating as compared to that of carbon in this case. Clear? There is no resonance picture coming here. It is only inductive effect which you need to check out. So if you consider the inductive effect here, this is also plus I. Here also it is plus I. But the plus I with silicon present on it would be more stable. So therefore acidic strength would be this way. Conjugate base already had an equivalent resonating form, right? This way. If you try to push electrons towards it, it will lose its equivalent resonance, which is not good for its stability. Now, in case if we have an order where you have all the withdrawing groups, suppose all minus I groups, if at all I have to compare, like I have NO2 with CH2COOH and cyanide N triple bond C, CH2COOH, okay, ETO, C double bond O, CH2COOH, MEO, CH2COOH, and OH, CH2COOH, and finally CH3COOH, which means H. Basically, we are comparing NO2, cyanide, C double bond O OAT, that is ester. This is OME, ether. Okay. Then alcohol with hydrogen. So if you compare their pK values, okay, experimental values I'll give you, that will also help us understand how their inductive effect is. So this is around 1.68, 2.47, 3.35, and I think I forgot one more. This is 3.58. Let me write on that. 3.58. Next, OME is 3.53. Got it. OH is 3.83. 3.83. And this is 4.76. And one more I forgot is the aldehyde form. Suppose if you have MEC double bond O directly connected to that, it's CH2COOH. I mean ketone form. So this ketone form. So if we compare that, this is around 3. This is around 3.58. Okay, and this is 3.35. 3.35. Yeah. Now check this. Now check the order of inductive effect. If you check out minus effect here, you can see that NO2 is stronger than compared to that of cyanides, then compared to that of COOR, right? Then compared to that of methoxide OME. This is the only exception you will find here with ketone Me with OH and finally H. This will be the order. Now look over the important comparison. This is a very important comparison. Suppose if we have phenol, cyclohexanol, correct? Then I have acetic acid CH3, CH2OH and CH3COOH. Let me take this as A, B, C, D. And I'm trying to compare the acidic strength of these four. See, the way I work out here is first I'll try to find out which of them have, what properties after they form conjugate bases. This has O minus. Here also it has O minus. CH3, CH2O minus. CH3, C double bond O, O minus. See the way we have to compare here. Okay. Now, if you compare this here, everybody check this. First, try to compare here whether any of them have resonance or not. Now we can easily make out here we will have resonance support. So there is a plus M effect towards benzene, right? And here there is no resonance, no resonance, no resonance. Here there is definitely resonance, correct? Next, after resonance, check out which has equivalent resonance. This would has equivalent resonance. These four does not have that. Next, check out which is localized. Sorry. Which of the following are localized or delocalized? You can see this is delocalized, this is localized, this is localized, this is delocalized. Which means localized electrons are unstable. Delocalized electrons are always stable. That is what we have learned from resonance. So we can definitely say these two conjugate bases are less stable compared to that of these two conjugate bases. Okay. So if these are the respective conjugate bases A dash, B dash, C dash and D dash, then how should be the stability here? Stability, first I can say that D dash is more stable than A dash because of equivalent resonance, and A dash is more stable than B dash and C dash. Between B dash and C dash, we will see that exo and endo bonds. Got it? If you can see that we have OH here, not exo and endo bonds, inductive effect. If you check out this OH here and CH3, CH2 here, this is more pulling towards, this inductive effect. If you check out here, like this, CH2O minus, and if we compare that with CH3 CH2O minus. Got it? Inductive effect will run better in case of CH3CH2 as it is in straight chain here. Here it has to come through a restricted bond, so the inductive effect relatively would be less. When inductive effect comes from a restricted bond, the movement of electrons would be less. If it is coming from a non-restricted bonds, the movement of electrons, the flow of electrons would be easier. So plus psi of this would be more as compared to that of plus psi of this. Correct? So which one will be more stable here? So we can say that B dash is more stable compared to that of C dash. Okay, students. So now tell me, what will be the respective acidic strength now? D will be more acidic than A, then B, then C. I'll showcase the pK values for the same. pK values for phenol is approximately 10. Cyclohexyl is around this. This is around 20. CH3COH is around 4.76. Suppose in case if we have CH3 and I have NO2 directly connected to this, and CH, NO2 and NO2 connected to this CH2, then we have CH and NO2 connected to three of them. So we can easily make out which is more acidic. Here the acidity we are searching is between carbon and hydrogen, because the conjugate base which will form will have resonance stability. CH2 minus, N double bond O, O minus and plus. So you can see it will have a conjugate base stability. The same conjugate base stability will be here, conjugate base stability will be here. So which is the most stable conjugate base in all of these three? The last one, because it has more number of NO2 groups. So that's how the acidic strength would be. We'll follow for the cyanates also. CH3CN less acidic than CH2CN twice, less acidic than CH-CN thrice. Same logic. Suppose if you take CH3, C double bond O CH3, ketone. In the ketone here, we are checking about this carbon and hydrogen bond. If you compare that with respect to CH3, CH double bond CH2, alright? Here we are trying to compare with the hydrogen of this carbon and hydrogen here, correct? Now if you compare this hydrogen, carbon hydrogen with respect to this carbon hydrogen here, okay, this carbon hydrogen breaking bonds, then which one will be more stable conjugate base here? You can check out. We can get this as CH3, not sorry with this hydrogen, I meant to say with this hydrogen, it's sp31, yeah. So we'll get here as CH2, here we will get as CH2 minus and C double bond O CH3, while here we'll get CH2 minus CH double bond CH2. Okay. Now this would have better resonating structures, as oxygen will get negative charge on it, while here only carbon keeps getting negative charge on it. Clear, students? So in that case, this would be more acidic, as if you check out the stability order here, stability of conjugate base is more stable for this one as compared to that of the second one. In fact, if you check out the pK values for the same, the pK values of ketone is around 19, and while here it is compared with alkene, which is around 43. Next, if you compare CH3NO2, compare that with CH3CN, CH3C double bond OH, that is aldehyde, and CH3C double bond OET, that is ester. In comparison of that, we'll see NO2 will be more dominant. All of them are giving minus M as well as minus I. The most dominant out of them will be NO2, which has more minus A as well as more minus M. NH3 plus will be dominant. Only case NME thrice, which you have, that is slightly less. But all other cases, they are stronger. Like if you check out NH3 plus, NHR2 plus, then NO2, then NR3 plus. Here, because of that, alkyl groups, there is slight stabilization. In case we have just compared that, aldehydes are better than ketones, right? I mean esters. Same way, ketones are also better than aldehydes. I mean esters. CH3 C double bond O CH3. This is a keto group, and if you compare that with CH3 C double bond O OET, correct? And if you compare that with CH3 C double bond O NH2, suppose I'll take this as 1, 2 and 3 to compare. Here, when it comes to ketones, right? Although you might think, sir, this is more donating species, there is one phenomena called tautomerism, which is what we'll be studying next week, where removal of this hydrogen C double bond O CH2 minus will give you a very stable form here. This will get resonance stabilized easily like this to get CH3 CO minus and double bond CH2, and this resonance stabilization really helps this H plus to remove easily. Got it? While here also we are expecting the same, that this CH2 minus, if it goes, it will help. But problem is, from the oxygen also there is an alternate resonance which is happening. So that will decrease the intensity of this resonance. I hope all of you are following that. That's why when it comes to esters, they won't act very strong acidic in nature. Okay. Hence, if we check out the pK values for the same here, this is around 19 and this is around 25. And now coming to this one, when it comes to amide, now this is not this hydrogen which is breaking, okay, for acidic nature. You can see nitrogen hydrogen has lot of electronegative difference. Now you have to compare the kinetic acidity. So nitrogen hydrogen bond will have more polarity, so H plus will be removed more easily from this end, so that hydrogen would act more acidic. That's why if you compare the pK value, it is approximately around 17, right? So amides, on the other hand, see, amines are very basic in nature but not amides. Okay, amides are very neutral, they are very close to water. All right, so remember that. So based on this, tell me the acidity now, which is more acidic, right? First, the third one, that is amides are more acidic than 1 than compared to 2. If you take CH triple bond CH and CH3 triple bond N, now if we compare this hydrogen, this is an sp3 carbon, this is an sp carbon, but this is connected to a very strong withdrawing group. Okay, so both will compensate their effects, and you will see pK value of this and this is almost the same. Okay, important. CH3C triple bond will have almost same acidic nature as compared to that of acetylene. Now last one, if you have diesters, or in case if we have diketones, how do we compare that? Suppose if you have double bond O here, there is a methyl group on this side, methyl group here, and there are two hydrogens here. So let me call one of them as acidic hydrogen. One more is also a hydrogen. Okay, same kind of a structure here, except that this side we have OET. Got it? That is beta keto ester. This is a beta keto ester. And the third case here, where ketone is on both sides, that is diketone. So we have OET here and here also we have OET. Let me call this hydrogen as HA, HB and HC. And I'm trying to compare the acidity of this HA, HB and HC here. So which one will be more acidic, students? First one, because here resonance will only happen between, this minus charge will go this side, this minus charge will go this side, that's all. Resonance will happen on this side. But here resonance, although it is happening on both the sides, there is one resonance which will happen from ester also, this part of the ester. Here this side also there is a resonance happening, this side also there is a resonance happening, and plus M effect will only decrease the acidic strength. So if we compare that, the acidic strength of this, we can say HA here is more acidic than HB in compared to that of HC here. Okay, so let me write the pK values for our reference. The pK values for this is 8.8, this is 10.7 and 13.3. Remember, these are all more acidic than water. So if you add it in water, they will give H plus. Check out, water is 15.5. So next class we'll discuss more examples, and this time it is all about benzene cases. Benzene with OH group on it, benzene with COH group on it, correct? Like that. One or two important pointers, just let me write down as a note here at the end. We check out the pK value. pK value of HCN is around 9.3. Okay, and pK value of benzene, pK value of benzene is around 43. pK value of toluene is around 41. pK value of CH3 CH double bond CH2 propene is 43. pK value of ethane is around 60. pK value of ethene is around 44. And pK value of acetylene is around 25. If you ask me which out of all this, the most important pK value would be of acetylene while problem solving. I cannot everybody.